previously we have seen in the lecture that what do you mean by lump parameter analysis. So just a quick recap of lump parameter analysis, and then we will directly move forward to. So if this is a ball, right, and the temperature at this location, at this location, at any location, if you see, this is a copper ball, right? The copper ball is there, and the temperature at all the location is 70 degrees, say for example. So here what is happening, that the temperature is a function of, here what we can say, that the temperature, it is not changing with position. Okay, if you move in any direction, the temperature, it is not changing. But for example, if again after half an hour, if I measure the temperature of the copper ball, the temperature might have been reduced to, say for example, 50 degrees. Here also 50 degrees, here also 50 degrees, right? So here from this conclusion, what we can write, that the temperature is not a function of position. Here we can say that the temperature is not the function of position. Okay, at any location if you go, the temperature will be same, that is nothing but 50 degrees or say 70 degrees. But the temperature here, it is what, it is changing with time. So this, here the temperature, it is changing with time but not with position. So such case we consider this, that the system is behaving as a lump. That's why we call this as a lump parameter analysis, right? So now there must be some mechanism, right, to check whether the system is behaving as a lump system or not. So there should be some mechanism, right? Every time you will not take the thermometer and measure the temperature at this location, the temperature at this location or any location, and then conclude that the system is behaving as a lump system. So for that, there should be some mechanism, and that mechanism today we will see how to judge whether the system is behaving as per the lump system analysis or not. So what is the criteria that we are going to see, right? So in the previous session, we have seen the derivation in which we have found out the temperature distribution equation we have found out, right? This is the equation that we have seen in the previous session. So those who have missed it, please go and watch the temperature distribution. Today we will see the mechanism which will tell you that the system, it is behaving as a lump parameter, as a lump system or not. Okay. So this is the temperature distribution equation. All of you know, we have seen this. So let's move forward now. Now the dimensionless parameter HA divided by rho VC multiplied by tau. Okay, what is tau? Tau, it is nothing but your time. H is nothing but the convective heat transfer coefficient. A is the surface area. Rho is density. V is volume. And C is nothing but your specific heat. So here what I am doing, I am just doing some rearranging. Okay, some changes. So before that, just read the equation properly. Okay, so here what I am doing, H divided by K, this K is extra over here, so this extra K is compensated by this extra K, right? Now this A is, so this one term extra, that is K, that is I have compensated. Okay, right? Now this A is already there, this A is already there. Again I am putting some extra A over here, so this A is extra, so that's why this I am getting this A square. So this A and this A get cancelled, so this one extra term I am inserting, right? This V extra I am inserting, so this V, and initially I am having this V, so that's why I am making this at square, so automatically this V and this V get cancelled. Okay, so what are the extra term that I have included? I have included extra term, that is nothing but your K, extra term, that is nothing but your P, and the extra term, that is nothing but A. So these three terms I have taken. So just I have rearranged this equation. Okay, so HV multiplied by HV divided by KA in another bracket a square multiplied by k divided by rho v square into c, and tau I am keeping just as it is. Okay, so now v by a, so this is a new term that you are going to see today. V by a, it is called as characteristic length. So it can be denoted by small l, or it can be denoted by l suffix small c. So this is the characteristic length. So what is the characteristic length? Volume of a solid divided by surface area of the solid. Okay, please keep this in mind. The area is nothing but the surface area. So I am replacing this v by a by a new term that is called as l. L is not, okay, it is the characteristic length. So what I am getting? L h into L divided by k. So this bracket is over now. Next term, here you can see the square one, you can see a square divided by v square. What is this? Again, this a square divided by v square, the reciprocal, right? So what I can write instead of this, I can write a square by v square as L square, right? Same again, v by a is nothing but your L. So I am replace this term, this square one, a square by v square by L square. Now I am left with three terms. I am left with three terms. K divided by rho into C. Okay, so I am left with this term K divided by rho Vc. So if you recall the initial lectures of heat transfer, all of you have seen this K by rho C, it is nothing but the thermal diffusivity. We have seen this, what do you mean by thermal diffusivity, in the unit number 1. So what I will write, instead of K divided by rho Vc, I will write it and replace it by alpha. So this term is alpha, this is L square multiplied by tau. Okay. Now why we are doing this, why we are arranging this like this? For simplicity. Okay. So alpha is nothing but K divided by rho Vc. And what is L? L is nothing but the characteristic length. So this term we will be utilizing every time for solving the numericals. So characteristic length is nothing but volume of the solid divided by surface area, right? So in the numerical, this the problem may be for will come for sphere, it may be for the cylinder, it may be for the cube, or it may be for the flat plate. So we have found out the characteristic length for different geometries. Very simple, just substitute the value of volume, just substitute the value of area, and you will get the simplified answer like this. So it is up to you. You can directly remember R by 3 for sphere, or the other way you can insert the formula for volume divided by the surface area and then find the value. Okay, so it's up to you. So now this term, this non-dimensional less term, okay, we will see in details in the coming units, not in this unit. What do you mean by non-dimensional parameters? So this will be the part of the fourth unit, but for time being, just see this. What do you mean by non-dimensional? We will discuss it in the later units. So now this alpha divided by L square into tau, this bracket, it is called as a Fourier number. Okay, it is called as Fourier number, and it is denoted by FO. So what is this Fourier number indicates? Okay, there is a physical significance. Every number is having physical significance. You might have studied in fluid mechanics various number like Reynolds number. So in heat transfer, in the coming units, we will see the various non-dimensionalness numbers, that is Reynolds number, Prandtl number, and the significance. What is the use? So what does this Fourier number indicates? It signifies the degree of penetration of heating or cooling effect through a solid. Okay, it signifies the degree of penetration of heating or cooling. Means what does it indicates? The speed of heating or cooling of the object. So Fourier number, it indicates how fast the object will take the heat or how fast the object will lose the heat. This is what Fourier number tells. Okay, clear? So higher the value of Fourier number, faster is the rate of heating or cooling. So if your Fourier number is on the higher side, the object will lose either heat very fast or either it will cool very fast depending upon the environment which is it is placed. So I hope the significance of Fourier number it is clear. It indicates the speed of heating or cooling of the object, right? So this number, okay, this bracket it is replaced by the term FO, okay, that is called as Fourier number, right? So why we are studying this? We still not have got the answer to the lump system analysis. How we will understand whether the system is behaving as per the lump system or not. So that is nothing but the next part, and this bracket will give you the answer, right? Now this parameter is left HL divided by K. Now what is this HL divided by K? Let's see in the next page. Now the non-dimensionless factor HL divided by K, it is called as the Biot number. What it is called? It is called as Biot number and denoted by capital B, small I. Okay, this is how it is represented. So what is Biot number? Biot number, it is nothing but HL divided by K. I will just zoom this. It is the ratio of internal conduction resistance to the surface convection resistance. See here, you can see HL divided by K. How I can write? I can write this HL by K in this form: L divided by Ka, okay, plus 1 divided by Ha. Now this A term it is extra, so automatically this A and this A gets cancelled, right? So this extra term I have included, so there is no change in it. Now this H I am taking to the denominator side, 1 upon H, so automatically it will come to the numerator. So I am just rearranging this equation. Okay, so after rearranging, what I get? L upon Ka divided by 1 upon Ha. This is what we get. So if you recall this, okay, if you recall this formula, okay, again we are going back to the first unit. L upon Ka, what is L upon Ka? It is nothing but the thermal resistance due to conduction. Okay, clear? L upon Ka, it is nothing but the thermal resistance due to conduction, and 1 upon Ha, it is nothing but thermal resistance due to convection. So please recall the concepts of unit number 1. So what is Biot number? Biot number, it is nothing but it is the ratio of internal conductance resistance to the surface convection resistance. Okay, resistance offered by conduction to the resistance offered by convection. So that's why we can write down easily as HL divided by K. And what is L? L, it is nothing but your characteristic length. Okay, so I hope you are very much clear with the definition of the Biot number. So now what is the significance of Biot number? Okay, that we are going to see. As we have seen the significance of Fourier number, what is the significance of Fourier number? Fourier number tells the speed of heating or cooling. Higher the Fourier number, higher will be the speed of heating or the cooling. Okay, so Biot number will also have some significance, some use. So what is that use? Just see. So if Biot number is less than 1, lumped heat capacity approach can be used. Okay, so we will use this Biot number to judge whether the system is behaving as per the lumped heat capacity or not. Okay, so if your value is less than 0.1, if you find out the Biot number and it comes to 0.1, then lumped heat capacity approach can be utilized. With advantage for simple shapes, such as you can apply this concept to plate, different geometry like cylinder, sphere, etc. And what is the error associated with it? The error associated is very less, that is 5%. Okay, so that much we can take into consideration. So what is the parameter that is used to judge whether the system is acting as a lump system or not? The parameter used is nothing but Biot number. So what is your first step? Whenever a numerical is there given on the lump system analysis, you have to identify whether we can use the approach. So what you will do? you will find out the Biot number. If the Biot number is less than 0.1, then only you can proceed with the numerical. Otherwise, if it is greater, we will say that lump system analysis or whatever the formulas for lump system you cannot apply. Okay, so if I substitute this, the lump parameter solution. So if I substitute this, okay, what I will do, just I will go back. So I will substitute the value now in this temperature distribution equation. This is the temperature distribution equation we have seen, right? So here I will substitute the value. This bracket only we have taken. Okay, so what I will do, I will substitute T minus Ta divided by Ti minus Ta, that is equal to exponential minus Biot number comma Fourier number. So if you can directly write down this formula also, but you should know the value of what is the formula for Biot number and what is the formula for Fourier number. This you should know. Biot number, it is nothing but HL divided by K, and what is Fourier's number? Alpha tau divided by L square. So these two formulas you should be very much clear while solving the numericals. We will be utilizing these two formulas. One is the Biot number, one is the Fourier number, and the other one the Biot number. These two formulas we will be utilizing every time for solving the numericals. So I hope the mechanism through which we can judge whether the system is behaving as per the lump system or not is clear to you.